welcome back. Today is also going to be a really fun day. We're going to start with a whole morning of models, SIR models. And we're really lucky today to have Professor Sandeep Krishna. He's at the Simon Center for Study of Living Machines. Basically, it's at the NCBS. He's my colleague. And he has been working for a long time at this interface of ecology, dynamics, dynamical systems, and also viruses and bacteriophages. So we're really lucky to have him and look forward to hearing from him. Sandeep.
Thank you, Uma. Yeah, it's a real pleasure to be here. So my mandate sort of is to introduce you to certain kinds of dynamical models of infectious disease spread. In particular, you would have heard the term compartmental models, right? So Ansil told me I should. So yeah, I'm sure many of you heard of the term compartmental model. So my aim is here to give you an introduction. I've been told that many of you don't have a background in maths or anything, or physics or anything like that. So my aim here is not to give you a full mathematical introduction. I want to introduce you to more the logic and the concepts behind these modeling. And the title I've put up there is really what I want you to take away, if anything, from this, is more about what the logic of models are, what people are trying to do with models, and what you can and cannot do. It's also very important to know what you cannot do with models, and also to understand all the kinds of assumptions and the myriad assumptions that go behind setting up these kind of compartmental models. Okay? So please do feel free to interrupt me at any time. I'm happy to, since it's a very diverse audience, it's hard to anticipate what some people know and what some people don't. So if anything that I'm saying is confusing, please stop me at any point and just ask, okay? So just to situate what I'll be talking about, I mean, as you've seen in this whole workshop, there are so many things that go into understanding spread of infectious disease, right? And we are going to talk about only a very, very small part. We'll be talking about epidemiology, but even within epidemiology, we're talking about mathematical modeling. But even within mathematical modeling, we will be talking about only one particular kind. Maybe if I have time, we can talk a little bit about other kinds of mathematical models. But really, I will be talking about one narrow area in a huge range of topics that one needs to engage with to really understand spread of infectious disease or any public health crisis for that matter. So we are going to be talking about a certain approach to mathematical modeling of infectious diseases, which relies on tools from dynamical systems, trying to understand how things are changing with time. Okay, so a lot of the tools come from physics and mathematics and applied maths, but people have been over the years applying them to infectious disease. And I want to give you an example of how that happens. Okay, so to give you an introduction to compartmental models, I'm going to talk a little bit about malaria, because I'm not going to give you a complete and perfect history of either malaria modeling or compartmental models in general. But malaria is an interesting case where one of the first compartmental models sort of arose. And it's a case which I can use, I think, to make a couple of interesting points about it. So has anybody read this book? I'm sure some of you have, okay? Yeah, I mean, those of you who haven't, I totally recommend reading it. Of course, it's a little bit of science fiction and fantasy. It's not like the exact history of malaria, but it's a fun read, and it tells you something about Ronald Ross and his research. And it's a nice way, if you're interested, to get into it, and then maybe you can read about the real history also. But yeah, so I'm going to take you back to the late 1800s is when Ronald Ross really started making advances in understanding how malaria is spread, and in particular understanding that it was the female Anopheles mosquito. And soon after that, in the early 1900s, he came up with a simple compartmental model. So this is one of the first examples of a model, a mathematical model, used to try and describe the spread of a disease and to try and understand some things about it and how to tackle it. Okay, so what he did was he divided the human and the mosquito population into compartments. So the first thing to note is that compartments, so I'm going to start writing, various kinds of assumptions that go into models like this. So I'll keep sort of listing things over here. Compartments are not like rooms. Compartments in this context are abstract compartments, okay? They are abstract states of infection. So in this case, what he did was is there a stick or something I can use? Or a pointer? There must be a pointer somewhere. It's okay, it's not a big deal, but in case there's a pointer, I can. It's okay, it's okay. Yeah, it's fine. I'll manage for now on. So what he did was he looked at humans and he just divided them, the human population, into two compartments. The set of people who are not yet infected and the set of people who are infected. So susceptible and infected. Okay? The mosquitoes similarly were susceptible or infected or dead. Okay? On the time scales he was looking at, death of humans was not really an issue. So death and birth was not considered here, but death and birth of mosquitoes was relevant. So essentially what you're doing is you're taking different states of the infection. You could be uninfected, that's a state of infection. You could be infected, that's a state of infection. And as we discuss further models, you'll see people added more and more states, okay? So this is a sort of an abstract compartmentalization. It's not like the susceptible people are in one room and the infected are in one room. In fact, precisely the point is that they are all interacting with each other, and that's how an infection spreads. Okay? So the first thing to note is these compartments are abstract. They are states of infection. The second is, in all these models, and many models I will discuss, up to a point, a lot of models assume that everybody is well mixed. Okay? So all the infected people have access to all the susceptible people. So let's put that down for now, and later on I'll tell you how people relax some of these assumptions. So it's what's called a well-mixed system. And therefore there are interactions between infected and non-infected people, which is what allows, some of these arrows mean. It's because a susceptible human can encounter an infected mosquito that they can become infected. And vice versa, it's because a susceptible mosquito can bite an infected human that it becomes a carrier of the infection, which can then pass it on, okay? So these arrows sort of tell you the transitions that can happen for any individual who's in any compartment. A susceptible individual can become infected, they can recover. A susceptible mosquito can become infected because of biting, and it can die, and so on, okay? So what can one do with a model like this? The point is that one can actually start to write down some kind of mathematical equations to then tell you how the numbers of these different compartments, the number of people in this compartment, or in this compartment, or the number of mosquitoes in this or this, change with time. And it's very similar to writing a chemical reaction, right? So here is sort of a chemical reaction way of writing that a susceptible human meets an infected mosquito, and the result of that interaction is an infected human and the mosquito is still around, right? So it's exactly like a chemical reaction. You must have seen people write A plus B gives you C with some rate, right? And then they use various kinds of ways to write down a rate of change of the concentration of a chemical like this. Like for instance, they will write something like that. If any of you have seen chemical rate equations, you would have seen something like this. Right? There is some rate at which this reaction happens, and the concentration of the different chemicals, the reactants involved, are what drives the rate of change of this reaction. And in this case, it's negative because A gets consumed to produce C. So it's very similar. In a very similar sense, you can take these kind of chemical reactions which describe a compartmental model and write down some rate equations, okay? And these equations are what tell you how these populations will change with time. And this is what Ross sort of wrote down and tried to use to predict what is going to happen if there's a population of humans and a population of mosquitoes. How will the infection spread? How fast will susceptible go to infected? How many will be the infected? Things like that. Okay? So once you write down these equations, you can actually solve them in various ways, either mathematically or on a computer, and try and figure out what will happen. So, and I'll get into this in a little more detail when we look at, so right now I'm just introducing the ideas, so I won't derive everything right now, but we'll get into some of the details a little bit more. But what is the use of a set of equations like that? The point is that you can actually get some sense of what are the important parameters involved. So let me write down, for instance, these equations that are written over here. Let me start with these. If these are the kinds of chemical reactions happening, what are the kinds of parameters that would affect how fast this would happen, how often this would happen relative to this? So let's try and put some of this down, right? So there's a susceptible human and an infected mosquito, and it is going to produce an infected human plus the mosquito. So what kind of parameters would go in? One, of course, would be the rate at which mosquitoes bite humans, right? So let's put that down. So that's somehow often called A. That is somehow the rate per mosquito, the rate of biting per mosquito. But every bite is not necessarily going to actually cause the infection. So there's additional to this, there's some probability that every time there's a bite that the infection is actually transmitted, right? So people put that down. Similarly here, if you have an uninfected mosquito which bites an infected human, it can get infected, and the human, of course, remain infected. So what will come here? The same biting rate, of course, comes here also, right? It's the same biting rate that goes into both. But here again, there will be a certain probability. A mosquito will bite an infected human, but doesn't necessarily pick up, right, the disease. So here's another one. So this is something like a probability of transmission. And this is a different probability of transmission. One is from mosquitoes to human, and one is from humans to mosquitoes. So the point is you start to be forced to think about what are the kinds of parameters, and can you now measure these? Is it something you can go out and actually put a number on? Can you design an experiment to actually find out this number? Okay, but we'll see what you can do with these numbers in a second. Okay, the other one is this. So this is recovery, right? People call it R, but there is some rate at which an infected human, and here it was assumed that everyone infected eventually recovers. But if they do recover, there's a certain mean time, right? So this is something like 1 over the mean time of recovery. Can everybody read what I'm writing? More or less? It's okay. I'm also going to describe everything. And then there's this one, which was sort of the death of the mosquito. So this is just some kind of death rate, right, of a mosquito, a lifetime of a mosquito. So the one very important thing that Ross figured out from a model like this, in the model, there is a particular combination of parameters, which is this, which has a threshold value. If this value is above 1, the infection can actually spread. So imagine a situation where you have mostly everybody is uninfected. Let's say 1 human is infected. There's a large population with everyone healthy. 1 person is infected, but they're mixed and interacting with another population of mosquitoes, which is also uninfected. And there is a probability that this infected individual will infect a mosquito, which will then infect another individual or more, and so on and so forth. and this infection could spread. Or it could happen that in the time that it takes for the human to recover, they might get bitten a bit, but it doesn't really, because the probabilities and rates are small enough, the infection doesn't actually even spread to the mosquito, or it spreads to one mosquito, but that mosquito doesn't really spread it to anyone else, and it doesn't spread, right? So you can imagine that there is a sort of a threshold effect. And it turns out that in this model, there is a very clear threshold effect. There is a very particular combination of parameters such that if you're above 1, the infection will spread. If you're below 1, the infection will die out. What is this combination of parameters? You can try and understand it the following way. So you would have heard this. I mean, I'm sure you've heard this now many times. It's the reproduction number. It's the basic reproduction number. Okay? And the logic is as follows. You have, let's imagine one infected human, right? This eventually will infect one or more mosquitoes. We don't know how many. That depends on the parameters, which might infect another human, right? And the point is, over time, and this will eventually recover. So there is a certain amount of time that you have for this to recover. How much is that time? We've already given that time, right? That is 1 over r. So in the amount of time that that individual is infected, which is 1 over r, how many mosquitoes will it infect? Will this individual infect? And given all the rates and probabilities, how many secondary infections in humans will this one individual cause? And now you can imagine why this average number, we assume this is of course going to be a stochastic process, right? Each individual, if we're in this room, I'm infected, and I start shaking hands with some of you randomly over time, and I have like, say, 10 minutes before I recover. In 10 minutes, I might have shaken hands with like, say, 10 of you, and maybe there's a probability of 1 over 10 that I infect somebody. In that case, by the time I recover, I would have infected one other person. Now that person, assume they're more or less the same as me, and they keep moving around in the same rates as me, they will also infect one other person, okay? We won't look too far in the future once everyone is infected and recovered, but let's just assume the first few infections. So you can see each of us in the very beginning is infecting one other person before we recover. So you could imagine the numbers will remain about the same, right? As soon as it's more than 1, even if it's a tiny bit more than 1 on average, let's say I infect 2, but you get infected and then you infect 1, it's still a tiny bit over 1. As soon as it's a tiny bit over 1 on average, you can see how the infection will just increase and increase and increase and spread, right? On average. Forget all the stochastic process, but if it was a large enough population where this kind of process was happening, if I, in the time that I'm infected, infect more than 1 person on average, then that person will go on and infect more than 1 person, and you can see, at least initially, the infection will spread, right? That's the basic reproduction number. That's the concept of it. Conversely, if it's less than 1, suppose on average, I infect less than 1. What does that mean? Let's say 2 or 3 of us are infected and each of us are going around shaking hands with you. I might infect 1 person, he infects 0, she infects 0. So it's like, okay, it's 1/3. If it's anything less than 1, you can imagine how everything will die out, right? Because people are recovering faster than they're infecting someone else, right? Every time there's a recovery, the infection number goes down by 1. Do you replace that infection number by more than 1 or less than 1? That's entirely how diseases spread, right? So the point is, how do you calculate something like that in a model like this? Yes, yes. Yes, please.
It sounds vague, but why is that 1 by r? Why not simply r?
Oh, sorry. Yeah, we should just go over the units here. These units, so remember this is a unit of rate. This is like a rate, which has a unit of 1 over time. So r, the units are 1 over time. So it's something like the recovery rate. The recovery time is going to be 1 over that. That has unit of time. So in fact, r is really defined as 1 over the mean time. That's really the definition. If you know that the recovery time is on average 2 days, you will say R is equal to 1 over 2, day inverse. So that's, in general, all the things we're going to talk about, key things over here, and let's talk about this. So in equations like this, where there's just one thing which is going to another form, all of these rates will have a unit of 1 over time. In situations like this, where you're talking about two things coming together, you have to talk about these rates are rates per time per mosquito. Okay, so you have to think about the units a little bit carefully when you measure them and so on. But essentially, for a single mosquito, a single mosquito will have a certain rate of biting, so many bites per hour or so many bites per day. Again, there'll be a mean time between bites, which will be 1 over that. So similarly, for the death rate, this is a rate which will have a unit of 1 over time. And 1 over the death rate will be the lifetime of the mosquito, or the average lifetime. Does that make sense to everybody? It's okay? Yeah? Thank you. Units are very important, and in any kind of mathematical modeling, one very important way of seeing if you're making a mistake is to check the units of whatever you have and make sure the units make sense. Okay? All right. So let's think about this in this kind of model. I'll give you a sort of a heuristic way of trying to calculate the R0. So this is the calculation that actually comes out of a model like this. And you can actually calculate that mathematically exactly, but you don't need to use complicated mathematics. You can understand what that formula means even just by logic, just the logic that we have been talking about. So let's imagine, let's really go through this. So imagine there's one infected individual in a large population of susceptible individuals. And similarly, mosquitoes are all uninfected, right? We're starting with that situation. So the basic reproduction number R0 is very specifically about that situation. It's about the initial stages of spread of a disease, okay? It's not about, we'll come back to what happens later on as most of the population gets infected. But right now we're talking about a situation where almost everybody is susceptible and there's a small initial infection. So we have this one human that's infected. We know that they will spend about 1 over R time infected. And in that time, the question is how many mosquitoes will they infect, right? So if you think about each mosquito, think about every mosquito, that is going to bite. Per mosquito, there is a biting rate of A. So we know that A times 1 over R times B, that's what we put here. That's the probability for any given mosquito in the population to infect this person in that much time and get infected, okay? It comes exactly from the fact that we put this rate here. So there's a biting rate for that mosquito. This is the amount of time that it's going to bite, so that will be the total number of bites, A by R, and then you have to multiply by the probability that any one of those bites, each of those bites will result in an infection. So roughly speaking, on average, this is the chance that any given mosquito would bite this individual in time and pick up the infection. But then there's a certain number of mosquitoes, right? So we have to take that into account. So that's the M that goes over here. So you can start seeing parts of this coming together. But this is a two-step process in this model. The human infects the mosquito, and then the mosquito has to infect. So now we have to look at each of these mosquitoes and ask what's the probability that they will infect a human? Because the number we really want is how many will this one infected human, how many humans will they infect? Okay? And if they infect more than one, then the disease will spread. They infect less than one, the disease will. So now, so this was alive for 1 over R, and that gave you this. Now the question is, how many will each of these mosquitoes, any one of these mosquitoes that's infected, how many will they infect? So we can do a similar thing. We know the mosquito lives for this much time, because that's the lifetime. And in that time, how many people will the mosquito, and we do the same calculation, except we use this rate, right? So now we do AC. And to get the total number, we have to multiply that by that. So the total number that you will end up infecting over here will be m a squared bc by r mu, which is what's written over there. And you don't have to worry about the exact calculation here. The point is, yes? Yeah, go ahead.
Shouldn't it be C instead of B at the...
Maybe it is. That's the infection where this is where you're the human. Yes, you're right. Thank you. And this should be B. And it turns out this doesn't change. But this is correct. So does everybody understand what happened over there? Because what are you talking about here? The human gets bitten by a mosquito and the mosquito gets infected, which is this reaction. Thanks very much. Very good spot. Okay, so again, you don't have to worry about the exact derivation here. Okay, there's lots of stuff you can read about how R0 is derived from a particular mathematical model, but I hope you got the logic. The logic is any infected individual is infected for a certain finite time. In that time, how many more individuals will they infect? Okay, assuming that everyone is susceptible. Everyone else is susceptible. That's the key. Now, why was this so important for us? It was important because now you can start, firstly, the fact is there's a threshold. So to recognize there is a threshold, infections can die out. Just because an infection is there in a population doesn't mean it will spread. It really depends on how many people that infected person will infect. And the question is, what parameters go into setting that threshold? And therefore, what parameters can you target if you're trying to target an infection and say malaria, you don't want malaria outbreak to happen, what can you target? And now we know some of the things you can target. I mean, of course, some of it logically makes sense. The total number of mosquitoes matters. So if you can bring the number of mosquitoes down, that matters. The biting rate matters. But you can say a little bit more than just this logical statement. That you could say without a model also, right? But you can say a little bit more. One thing that was the fact at the time of Ross, when he was working with these models and first coming out, it was to some extent thought that if there is a population of mosquitoes, even a very small population, the disease will spread. But here you know that's not true. If all the other parameters are fixed, there is still a value of m, if you bring it low enough and you bring this value down below 1, even if mosquitoes are not completely eradicated, the disease will not spread, right? So the first fact that he was able to use from his model is to say that there is a threshold in a lot of these, all of these parameters. You don't have to completely eradicate everything in order to make a disease not spread. You only have to bring it down below a threshold. Now, you can also go further and say which of these parameters are most useful to get after, right? You could reduce m, but you could try and reduce a also. So now we're getting into more practicalities. Mathematically, you can see that something that comes in with a square is probably a good parameter to target, because a smaller change in that will cause a bigger change in the overall reproduction number, right? If there was a nice way of targeting a decrease of a by half would cause a decrease of 4, a factor 4 in the reproduction number, whereas a decrease of m by a factor 2 would only decrease it by a factor 2. Now, whether that's practical or not is another issue, but the model tells you that certain combinations of parameters are important and tells you which parameters might be the best to target. It also tells you what kind of experiments you might want to go out and do, what kind of data you might want to go out and collect. Now you know that biting rates are important, the total population is important, the lifetime of mosquitoes is important. Maybe you can actually go out and try and measure some of these things, okay? So these were very early days of modeling of this kind of disease. And it was sort of this, at this level, very basic, logical level, some of which you could even just argue without the mathematical model, just even logically. Once I've shown you how the mathematical model behaves, these results are not surprising, right? You can actually argue this even if you did not know the details of your mathematical model. Some of these facts are true. Even if the way of transmission was more complex or simpler, many of this would still hold true, and the fact that there is a threshold, you can see logically still holds true, okay? So we begin to learn something about this. Okay, let's move on. So we talked about this basic reproduction number, but as I said, the basic reproduction number only tells you about, the basic capability of this infection to spread or not in a situation at the very beginnings of the infection, where the infection has a lot of susceptible individuals that it can actually access. But what actually happens over time? If we were a population, and we're talking about spread here, so initially, yes, let's say I went around, shook hands, I infected somebody, and I infected 2 people, and then they on average went and infected 2 people. Over time, more and more people would get infected. Now suddenly, the person who's getting infected, when they're going around doing handshakes, they're meeting often as many other infected people as susceptible people, right? So in that kind of situation, the probability of now infecting more and more people has to go down because the number of susceptible people you're encountering is less, right? So indeed, that's what happens. So while the basic reproduction number kind of tells you what happens at the beginning of an infection spread, over time, a model like this, what is going to happen to a model like this? You can imagine over time that you first start with a high number of susceptible people, a small number of infected. Here, let's say we're just plotting the human side of it. The number of susceptible people will go down, the infected will go up, and at some point, you will reach a level where as fast as the susceptible people are getting infected, the currently infected people are getting recovered, and you reach some kind of dynamic balance, right? In a simple closed system like this. We're making many assumptions here, but in a simple model like this, you will reach a dynamical balance where each infected individual doesn't have access to as many susceptibles as there were in the beginning. So even in the beginning, if the individual was infecting more than one, in practice later on, it's infecting less than one. So what happens over time? Over time, as I've written over there, your susceptible population is a function of time, right? And your susceptible population is going down. And let me write this as the fraction of the population. It turns out that this number, or since it's all S, this is just confusing. Let me just write it like this. This quantity is sort of at any given time the effective reproduction number at that time. So in the beginning, when the susceptible population was the whole population practically, this is practically 1, and your reproduction number is R0. So when I'm infected and all of you are susceptible. But over time, many of the susceptible people are infected now, and now if I'm infected and I'm trying to infect various people, or not trying, but it happens, half of my interactions will be with, say, infected people. If S by N is half, then the number of new infections that I will create will be half, okay? So this fraction very much affects, at a given time, how many you will infect. And as we said, the logic still remains that the infection will spread. That means the number of infected people will go up when your reproduction number is more than 1. If your reproduction number is less than 1, it'll go down. So eventually, what happens in this part is that this effective reproduction number reaches 1. It starts off larger than 1. That's why the infection spreads in the first place. This is an example where R0 was larger than 1. If R0 was less than 1, the infected population would have just died out. Here, the infected population has increased, and as it increases and the susceptible population goes down, let's say this started off as 2. Then this population of susceptible has to go down to the point where it becomes half, at which point this will become a net of 1, and that'll be your steady state, okay? And in this kind of a scenario where the recovery goes back to S, we'll come back to other kinds of situations, but here you're talking about a situation where when you recover from an infection, you go back to being susceptible. We know for many diseases that's not true. You might have immunity, That's a different scenario. But in this scenario, you reach this dynamic equilibrium where every infected person is infecting just one, and these new infections are just balancing the recoveries, and everything reaches some stable state. Okay, so you can get here. So one needs to keep in mind the basic reproductive number, and then the current reproductive number, or the effective reproduction number at any given time. Okay, so I want to make a few comments about a model like this. When Ross made a model like this, you're used to seeing, I think, mathematical models which are designed to take a lot of data and fit it, and all these complicated fits, and you pull out various things and you make predictions. This is a model which was produced at a time where there was hardly any data. Okay, there was only some basic facts actually. The fact that the female Anopheles mosquito does this. There weren't even great measurements of some of these parameters. So what use is a model? A model can nevertheless be very useful in a situation where there's very little data, like this model, because it helps conceptualize the problem. It helps tell you what are key parameters to think about, what are key combinations of parameters, like this. So the fact that in this simple model, this particular combination of parameters was very important, tells you that in some ways you don't need to know all of these parameters independently. If you could measure particular combinations, if you could measure them separately, great, but if you could measure particular combinations, this is the combination you really need to know. So any which way, if you can get this combination without measuring the underlying parameters, that's also fine. So it kind of tells you, what kinds of experiments to design, what kind of data to collect. It tells you some basic insights. The fact that there is a threshold itself is a basic insight, which may go on to also apply to other kinds of models which are more complicated and more realistic. Okay? But of course, everyone is interested in predictions, right? I mean, I think you all saw during COVID, there was a huge uptick of how many modeling papers were like coming out there. I think I have a graph, yeah. So they published like how many modeling papers. And I mean, it was just everybody who could write down 3 differential equations was modeling COVID, right? I mean, me too. I hadn't worked on infectious diseases. I'd worked on bacteriophage, but I also got involved. I mean, maybe it was such a uncontrollable situation. It was a way of sort of feeling a little more in control. But a lot of people came in, but you could see that in the modeling, just as with Ross, we were dealing with a disease where initially there was very little data. There was not much known. You could make simple models. And you could, from simple models, get some basic insight, which is not too far from what we've seen with Ross's model. But that's not what people were interested in. From all the headlines and all, people were trying to model the exact way the things will go up. Exactly how many diseases will come up every day? Is it going to be 10,000 new cases per day or 1,000 new cases per day? Where is the peak going to come? When is the peak going to go down? I mean, naturally, because that's what people were afraid about, right? Are these models good for that? Is a model like Ross's good for that? The simple answer is no. It is not good for modeling or predicting such minute details, the precise things. And I'll talk about this a little more. And people went on even with Ross's model, went on to produce more complicated models. Why is it not a good model to predict such precise curves of how populations are susceptible and all will go up and down? It can predict qualitative features, but not precise features. Why? Because it's missing many things. One of the things that it's missing, which some of these later models try to put in, is that there is a latent time after infection, right? You get infected, but that doesn't mean you're immediately infectious. There is both for humans and for mosquitoes, okay? So these guys tried to put in the latent time for, I think, the humans. I forget now, maybe the mosquito. And these tried to put in the latent time for both. But there are also further things to put in. There are many more details in the actual spread of a specific disease that go beyond a simple compartmental model like this, which you need to start taking into account if you want to do a more detailed prediction. So we'll come to that. And what I want to tell you a bit about now in the next few minutes is the ways in which people add realism and more complexity to these compartmental models. But let's step away from the humans and mosquitoes and malaria for a bit, because it's a slightly more complicated situation where there's two populations. No? There's a vector and a host. There's the humans and the mosquitoes. Let's just talk about just humans. Okay? So there are viruses or other diseases where it's just human directly infecting another human. Let's talk about those. So the simplest compartmental models that were made were sort of very similar to this, except it doesn't go through the mosquitoes, it's just directly infected. So as I mentioned before, one complication that this kind of a model does not even begin to address is immunity, right? And you know there are many diseases. There are diseases for which this is sensible, that the infected, once they recover, are susceptible again. But we also know there are many diseases where there's also, if you recover, you have immunity, at least for a certain amount of time. So people started making models like this. And this is the famous SIR model many of you must have heard about or read about. So this is a model in which there's susceptible compartment, there's an infected compartment, and there's a recovered compartment, right? So in this one, essentially, over the timescales we're interested in of this infection spread, once you have recovered, you have immunity. So you're not going to get infected again. So in a sense, you're just taken out of the whole game, right? And this causes a qualitatively different picture, and you can see that. Without doing any modeling, you can see that qualitatively the curves and the results have to be a little different in the sense that over here, the susceptible started high, came down, and reached a dynamical equilibrium with the number of infected, right? That's because the infected, when they recover, go back to being susceptible and can get infected again. But over here, you know that once you're recovered, you're out of the game. So the typical structure over here is the susceptible go down, the infected go up, but at some point, there's just no more susceptible left to infect, and the infected are recovering. So the infected will go down. So there will be a peak, it'll go down, and the recovered population will go up. And this is true of COVID, at least for one wave, right? Any one wave, it was sort of like this, that people were not getting, very rarely were people getting COVID from the same variant again. Not that it's impossible, but it's a good approximation that you were in some kind of situation like this. So you can write down similar equations for this. And it turns out, you know, a similar logic applies for the basic reproduction number. There is a basic reproduction number you can derive here. There is a threshold. It's the same logic. Are you going, the infection will spread if you're going to spread to more than one person on average in the time that you are infected. But eventually, there is a recovered population that sort of just builds up and builds up and builds up. And since they're immune, eventually the infection has to sort of die out. Okay? As opposed to here, where it reaches a dynamic equilibrium. All right? So, so in this sort of the first half of the session, or maybe a little bit into the second half, I'll be sort of telling you a bit more about more complicated models, some of the work we have done, some of the kinds of things you can do with mathematical models. But in the second half, I want you to actually try and play a little bit, you know, with some models. And since this is one of the simpler and easier ones to understand and an easy one to sort of play with, what my plan is to give you access to an applet. Let me see if I can show you that applet now. Hang on. Yep, it's somewhere here. So here's a little applet. So you don't have to solve the things, but this is a little applet which shows you a simulation of an SIR model. Okay, so you start off with some susceptible, you start with a small number infected, and then as we were talking, the infected goes up and then goes down, the susceptibles go down, and so on. And it's a population of, you know, some things are fixed about the applet you can't change. There are 10,000 people, but you can change certain parameters. So towards the end of this, we can try and play with this after I've talked about, you know, the kinds of things people do with models. Perhaps you can play with this, and I can set you some questions of like the kinds of things you can do. What can you infer? Suppose this was a disease. This described a disease that was actually going through the population, and you had access to some data. You could take measurements of this population at certain times. How much could you infer back about the disease? How much could you infer about the transmission rates? How much could you infer about where this disease will end up? Okay, so did everyone get the link? I think Ansil sent a, yeah? So at some point, maybe in the break, please have a look on your laptops if you can click on that link with the HTML file. And if that opens up this little applet and it plays, and you can run with it, okay? And if not, then I think we have the files, we can give it to you if it's not working through the link. So if you have that, then I'd like you to play with it. So let me just take a little pause here before getting into a little more of the details of how people complicate some of these issues. I want to tell you a little bit more about the SIR model, okay? So we have about half an hour, maybe some of that time I'll spend telling you a little more about the SIR model. So you have at least one model that you've seen in a little bit of mathematical detail. We're not going into too much detail to make it very, very complicated, but just give you a brief sense. So for those of you, who have previously worked with differential equations and stuff, this is going to be very simple. But for those of you who haven't, it's not going to be too complicated. Okay, so let me rub this out also. So what does an SIR model look like? As we've said, there are three compartments, right? There is susceptible, infected, and recovered. And we want to write down equations to describe how these change with time. So the first is, so it's again very much similar to what we've talked about. So this is the rate of change of the number of susceptibles over time. And it's usually written like this. Okay, let's go into this a little bit more. It's very much related to this. So S, and a susceptible individual meets an infected individual, and then you end up with two infected individuals. Okay, this is sort of like the chemical reaction way of writing it. And it's parameterized by, just as we did with the mosquitoes and the human infections, by a certain rate, an overall rate. And that rate is written, so the rate at which this whole reaction happens, of course, depends on how many susceptibles there are. It also depends on how many infected there are. Okay, it has to depend on both. If there is no infected individual, then of course a susceptible individual can't get infected. If there's no susceptible individual, also there is no susceptible individual existing to get infected. So you can see how if either of these are zero, this whole rate is zero. So you need the existence of both susceptibles and infected to even have some rate at which susceptibles become infected. Yeah.
I had this one doubt.
Yes.
So there is one additional parameters that, I mean, you have considered the number of population which has recovered.
Yes,
right?
yes, correct.
But sir, logically seeing through it, that is an indirect, I mean, susceptible, number of susceptible hosts is an indirect measure of how many recovered patients you have,
It
right?
can
But
be.
why do you have to?
So the key is here, the difference is in this model versus this model. So you're right. So it's not in itself. In itself, you're absolutely right. In some sense, you don't, in this SIR model, the total number, so let's say S plus I plus R is going to be a constant. So if you know the number of S and you know the number of I think that's what you're trying to say, then automatically you know the number of R. So you're indeed, this is not independent. It's not an independent number that you need to know separately. If you know any two of these, you know the third. So that's absolutely true. But what is different in this scenario versus this? In this scenario, you have S plus I is equal to N, right? You're either susceptible or infected, and here you have S plus I plus R is equal to N. So in this case, you need to know any two, you know the third. In this case, in fact, if you know one, you know the other. Okay? But the point is, the qualitative behavior of how these populations will change is very different because of the way these interactions are in these two cases. And the fact that there exists a recovered population has a real and qualitative I mean, forget quantitative. It has a real qualitative impact on what the final outcome will be. Because there is a state in which you are immune to further infections and permanently immune in this kind of model, that means that anybody who gets immune is no longer ever going to get infected, and that has to be the final state of the infection. The final state will always be where there is no infected person left, and there are only susceptibles and recovered left. So in this case, the final state always has to have I is equal to 0. Just logically, you can see that there will be some susceptibles will get infected, but any infection that goes into R just gets absorbed, right? That person is out of the game. And eventually all infections, because the only source of infections are susceptibles, eventually, once you get down to a low enough number of infections, they will infect somebody, they'll recover, and eventually either there will be no more susceptibles left, it'll go to 0, that could happen, but it can also happen that this goes to 0 before that goes to 0 and some are just left over, and you only have susceptibles and recovered. In this case, that's never the case. Because you go back to being susceptible, you usually reach this dynamical equilibrium, which I showed. Let me go back. Here you get this dynamical equilibrium, right? So it's not that you need to keep track of R necessarily in these models, but you can make do by keeping track of an SNI, but the behavior is very different, and that's the key important part. So they are qualitatively different models because of the qualitatively different behavior they produce. And logically, that's, you understand, it's because of immunity. Yeah.
In the SI model, the initial assumption itself is kind of, vague, because after getting infected, you are saying that after getting recovered, you are once again considered as a susceptible host, which might not be true for many diseases.
Absolutely. So for diseases, it's not true. That's not a good model. So this is precisely why this model, to some extent, makes sense for mosquitoes, and that's why it was made for malaria. But it's not that you can take a model that works for malaria and automatically take it to another model. Okay. And indeed, this is one of the reasons why many different kinds of compartmental models exist. So this was one model. So the very fact that I'm introducing this is already there are two types now, I'm saying, of diseases. These are diseases where the infected recover but are immediately susceptible again. Here are diseases where you recover and you're permanently immune. Of course, there are many in between, right? So you could have a third class or a more general class, you could say, where there's a recovery and then it takes a certain time to become susceptible again. And that certainly, people study that. So it again depends on the timescales you're interested. If the loss of immunity time, it's often, in many cases, it's much, much, much slower than all the processes happening here. This might be happening over, weeks, whereas that loss is over a year or something. Then you don't need to worry about it. But if the loss of recovery is on the same time scale as the processes of infection, then you do need to worry about it. If it's very fast, then you can just ignore it and forget about that compartment. So the choice in all these models, so indeed, I mean, there are many choices made. Let's put that down. Choices about, how many compartments and what do those compartments mean is very much part of modeling, making these kind of models. Okay? Do you include a recovered compartment or not? Do you include something in between? And I'll tell you about that. I'll tell you a little more. Let's talk a little more about SIR, and then I'll come back in the second half to more complications that people put in. Okay? So, so this is the rate at which you get infected. And this is a sort of a convention to put the n in, so that this has a unit of 1 over time. Okay? But this parameter beta, it includes both the contact rate, the probability, the rate at which people meet each other, which is then also dictates the rate at which there will be encounters between infected people and susceptible people. So this includes contact rates and probabilities of transmission. So just as we did with the Ross model, there we more explicitly put in something like A, B, and AC, where this was the rate and this was the probability. Here, they're sort of combined into one because there's only one parameter, they always occur together, so people think of them as one. But essentially, this parameter includes both. So keep that in mind, that it includes both, so again, in the analogy of me going around doing handshakes, it's like how many handshakes will I do per unit time, and multiplied by the probability that I will actually transmit in any of those handshakes, right? In any given. So both are combined into one parameter. Okay, then we have to do the infected, which is this. So whichever term reduce the number of susceptible, that same term comes here with a plus sign, right? Because what's happening? The susceptible, this reaction in which a susceptible met an infected and became infected, that decreases the number of susceptible and it increases the number of infected. But there's another one, which is the recovery. So we have to add one more term here, which is this, which is the recovery rate. And again, this has 1 over time. So 1 over gamma will be the mean recovery time. Okay? And as we discussed, you actually don't need to keep track of the R because you'll know it, but you can do it. You can write it down anyway. And that will be just that part. That's the recovery. So this is your basic SIR model. That's it. Okay? And on the face of it, it seems to have 3 parameters. It has this beta, it has gamma, and the other thing that it has is n, which is the total population. Okay? So you can imagine you can change each of these parameters independently and ask what happens. Okay? So this is your basic SIR model, and when you play with this applet that I showed you, that's what the applet is doing. Actually, I'll tell you, the applet is doing a little bit more, but it's more or less this. The applet is doing a stochastic version of this. So another assumption that sometimes comes in is many of these models are deterministic. Many of these models are written as differential equations, rate equations like this, where there is a rate of change, which is this. If you take this model on the face of it as is, and you simulate it or run it, if you start with the same initial conditions, you'll get the same output. There is so far, there's nothing in this which allows for noise. And as you know, in any real situation, of course, the spread of infectious diseases is noisy, especially in the beginning phases. When usually noise has less of an effect when there are large numbers. Okay, when there are plenty of infected people and there are plenty of susceptible people, and we're talking about encounters, right? Chance encounters, there is a rate that defines on average how often these encounters happen and how often a transmission happen, but each event is actually stochastic, right? And these probabilities are a sort of average way, these rates are an average way of describing these stochastic events. So when there are lots of such events happening, an average is a good description. If there is a probability of 0.1 of something happening, like a transmission happening every event, if there are 10,000 events, yes, it's probably going to be that there will be 1,000 transmissions. But if there's only one event, then in one scenario there might be 0, in another scenario there might be 1. So there is much more noise and variability when you have small numbers, okay? And a lot of infections do start with small numbers, after all. Small numbers of infected, at least, usually. You usually have large numbers of susceptible, but small numbers of infected. So very often in the initial stages of an infection, there is a lot of noise and variability. Some infections, even if you've measured all your average reproduction numbers and everything correctly, just by stochasticity and noise and variability, sometimes an infection that starts with just one infected person, just by chance may not take off, even if on average that person should have infected 2 others. But maybe it just so happened that those days that they were infected, they didn't go out much or something, and they didn't infect. On the other hand, infections which are just below threshold, sometimes by chance could get to spread a little bit before they die out because of chance events. So you have to take all this with a little pinch of salt and know when this deterministic assumption is a reasonable one and when it's not. And I'll come back to how people put in noise now. So when you're really worried about the noise and this stochasticity, how do you put it back into models like this? So we'll talk about that. But for now, let's just take this. So this model is a very, let's use about 5-10 minutes to go back to those questions, the things I had told you about the Ross model, and just see it play out over here, okay? So here, because it's a little simpler and you're not dealing with mosquitoes and so on and another set of populations, you can actually go quite far and see a lot of the mathematics. Even if you're not very familiar with the maths, you'll actually see quite a bit. So as I said, there seem to be 3 parameters, right? There's beta, there's gamma, and there's n. But it turns out that's actually not the case. So there's a very neat trick when you have equations like this, which allow you to reduce parameters. And the trick is that you can sort of choose the units in which you decide to measure things. So we are going to actually change the units of things a little bit. See, if you have a dynamical system and you're measuring how something changes with time, let's say number of infected people versus time, it shouldn't matter whether I choose to describe time in days or hours or seconds. I can choose whatever, right? I'll just change the numbers. So suppose I was measuring time in hours, but then for some reason I decided to measure time in days. So I want tau to be related to t, but in days, the same number of days. How do I do that? I just multiply by the appropriate number, right? So if t is 24 hours, tau should be 1 day. So tau should just be t by 24, right? So if t is measured in hours and t is like 12 hours, then tau would be 0.5. So it doesn't matter whether I have t as like 12, 24, 36, 48, or tau as 0.5, 1, 1.5, 2. It shouldn't matter which unit I use, right? So that allows me, and similarly with numbers, with the population, it shouldn't matter whether I'm talking about the number of susceptible and the number of this, or I decide to talk about the fraction. So I'm going to define some new variables, which will be this, which is just the fraction, and small r by n, and I will define tau to be beta t, okay? You just need to make sure the units are okay. Beta has a unit of 1 over time, because it's a rate. T has unit of time. So this has no units, okay? It's unitless. It's just going to be a number, but you have to remember it's related to that rate. I'm just going to use it as a way of getting rid of some of the complication, that apparent complication of those equations, okay? Now, if I use these and rewrite all these equations, I get these much simpler equations. And I'll show you how in a second. Let me just make sure I have it. I write these correctly. Okay, so this is pretty much the most maths we're going to do here, all right? So hold on and follow along with me. So how did this happen? The way to get those equations from here is if you just multiply everything. So if I just divide this by n, and I wanted to multiply this by beta on both sides, so I multiply this by beta and n, right? Now you can see this n can go in here and become small s. This can go in here and this becomes tau on the left. This beta will cancel with this. This n will combine with this to make small s, and this will combine with this to make small I. So it's just multiplications, all right? But the key thing to remember is all I'm doing is choosing the units with which I measure things, units with which I measure time. But the advantage is, look, the equations look a lot simpler. And the one thing, so the point is, if I run these simpler equations, I can always get back the behavior of the more complicated equations by just reversing this. So if I solve this, and I want to actually know how the infection spreads in days, I just go back and I re-multiply. I can find t from tau by just dividing by beta and so on, right? So there's no difference between the behavior of these equations and these equations. It's the same system. But the big advantage here is you can see that this combination always occurs together. And so you don't need to, so you've learned two things. You don't have three parameters. You can actually work with just one parameter, and that one parameter is all that matters and describes the entire behavior of this whole system. If you know that one parameter, you know how the system behaves, because you can always go back, and for any case here where there are three parameters, you can always figure out which particular value works, okay? You can work it all out. What is this parameter? Can somebody guess? Given everything I've said before, it must be related to R naught, right? And it is, in fact, related to R naught. It's actually 1 by R naught. So let's just list out the facts here. 1, gamma by beta, which is 1 by R naught, is the only parameter that matters, okay? That's something we've learned, okay? Does it make sense that R naught, I'm calling it R naught? We had defined R naught in a certain way, right, logically? R naught was what? In the time that a single individual is infected, assuming everyone was susceptible, how many others would they infect? Let's try and work it out independently. How long is an individual infected given this, all these parameters? Somebody? 1 by R? There's no R here now. 1 by gamma, absolutely. Okay, so 1 by gamma is the time in which it's infected, and in that time, how many will it infect? It'll be beta, right? So beta by gamma is exactly that number that we were talking about, okay? So in a way, given everything I told you, it's not surprising that we came down, but now you can go back and see all the things that I was saying about the Ross model. In this simple model, it's very easy to see. You can see now why there is a threshold. If you look at this equation here, all you have to see, so it's S into I minus I by R. Initially, what is S? When you start the population of, S is the fraction that is susceptible. It's close to 1, right? So assume it's 1. Then what are you left with? At the very beginning of the thing, it's 1 minus 1 by R0, right? Now you can see why there's a threshold. So what we were talking about a threshold in the sense that if R0 is larger than 1, then the number of infected will go up. If R0 is less than 1, the infected will go down. You can see that, you can just see that straight from here. If R0 is smaller than 1, that means this quantity is larger than 1 and this whole thing is negative. So di by dt, the rate of change of infected, is negative. So it has to go down. That means the infection is not spreading, it's dying out. If R0 is exactly 1, this is 0. So that's the point at which it'll just stay going. If it's larger than 1, then this is smaller than 1. 1 minus that is some quantity, but it's positive. So this whole thing is positive. So the infected will go up, okay? There's another thing you can see, which is so there is a threshold in R0 for infection. So we had discussed this more qualitatively earlier, but now you can see it a little clearer in this simple model. Finally, in this same situation where the infection is initially spreading, the equation is for I is quite simple, right? Let me write it over here. Let me rewrite it. So let's assume in the very beginning, the number of susceptibles are practically 1, I mean practically the full fraction. Then di by d tau is I 1 minus 1 by R0. This is a particularly simple equation, which even if you have not done much maths, you might recognize as something that will produce exponential increase, okay? The solution to this equation is I of t is I of 0 e to the power 1 minus 1 by R0 tau, right? Because tau is the way we're measuring it. So again, this is not hard to understand. You can imagine we were talking about this reproduction rate. If I infect 2 people on average, and then those 2 people infect 2 people, and they infect 2 people each, of course it's going to be exponential. It's going to be 2, 4, 8, etc. So you can kind of see, but logically, but here you can see it explicitly. It will be an exponential, and you know the rate. And you know how the rate of the exponential depends on R0. Let's be a little more explicit. Let's try and take this back to the time units in which we actually started and measured. So we know how all our parameters come in. So remember, I had tau was beta t. So if I now put all the things back, all the parameters back, this is 1 minus gamma by beta t, right? Which is beta minus gamma t. Right? So not only do you know, so you know that it's going to go exponentially. If you know the R0 or you measure the exponential very well, you can get R0, right? If you know R0, you can try and predict how quick this exponential will be. If you don't know R0, but you know these parameters separately, you might have measured the recovery time of the person. You might have measured the rate of transmission. If you know those, you can get that. If you know any 2 of these, suppose you know the rate of recovery and you've measured that initial exponential very well, you can use that to try and calculate beta, right? So these are a few things you can get from it. So the third thing that I want to put down here is I initially is exponential. Exponential, and it specifically with a rate 1 minus 1 over R0 beta t. Okay? So we've learned a few things about the SIR model, and it's almost a time for a break now. So what I'm going to do is sort of stop here. And does anybody have any questions? Yeah. You wrote that equation exponential. Yes, yes. How do I get this? Exponential. This one? Yeah, yeah. Let me give you a quick sense of how you get that. I think, let me do it here itself. Okay, I'll do it above. This is a sort of, it's a very more general thing. So if you have dx by dt is some alpha x, okay? This equation always has, I mean, you can actually derive it. The easy way to derive it is you bring the x that side. You have something like dx by x is equal to alpha t. And that already gives you that x of t is x of 0 e to the power alpha t. Okay? That's the quick way of deriving it. But I mean, you don't, the mathematical derivation is one thing. What's important here is the logic. If the rate of change is proportional to how many there are at any given moment, then that's always an exponential process. Because as you increase, you also increase the rate. So in the context, so think in the context of infectious diseases, if the number of infected people is 1 and each is infecting 2, that's the rate. The rate is how many you infect per time, in some sense. If one person infects 2 per unit time, then they become 2. And then those 2 will infect, each will infect 2 per unit time, so they'll become 4. And then those 4 will each infect 2 per unit time, so then they'll become 8. So essentially, that's where the exponential comes from. Anytime the rate of change is proportional to how many there are, you have an exponential process, whether it's exponentially decreasing or exponentially increasing. You might have seen, some of you, in radioactive decay is another example where it's like this, except it's got a negative sign. Or any kind of chemical decaying. And that's also an exponential. Each molecule has a certain chance of decaying or a rate of decay, and therefore the total rate of decay for n molecules is proportional to how many there are. And then you get an exponential again. So exponentials come in wherever your rates are proportional to how many there are. And in this case, that's the case. The rate of increase of the infections is proportional to how many infections, and that just goes up there. So in a model like this, essentially you get some basic qualitative features. So let me list that, and then we can stop and take a break and then come back. Yes. So for R naught exactly equal to 1, what will happen is that essentially you're over here initially very close to the beginning of the infection, your number of infected will remain constant. So essentially you're in a state where the number of infected, like say there's one infection, that will cause one infection and this one will recover. So you're now in a state where there's one infection and that will then infect one person and this one will recover. So that 1, 1, 1 will go on for a long time. Now it won't go on forever. That's just in the beginning, it's like this. Eventually it can't go on because all those recovering ones are eventually going to suck away the susceptible population. So eventually, if you had R not exactly 1, even that would die out in a model like this because eventually the recovered go down. So remember, I had told you about R naught and R of t, the current one, right? So in any of these infections, R naught just tells you the very beginning. And then usually the susceptible population goes down, so your effective reproduction number starts to go down. So if you start high, if you start above 1, the infection initially spreads, the susceptible population goes down, and the effective reproduction number comes down and hits 1. It started above 1, so it'll come down, come down, come down, and hit 1. At that point, your infection will stop spreading. Where is the point? Here, that point happened over here where a dynamic balance was reached. Let's talk about what happens in the SIR model. Where would that be? Where would be, so let's say this was a case where R naught was larger than 1, but over time, as the susceptibles went down, the effective reproduction number goes down, and at some point the infection stops spreading. What is that point? That point is exactly here. This is the point where R is equal to 1, the effective reproduction number. That's where it peaks. After that, it's all downhill in this case because R keeps going down. In the SI compartmental model, R starts at R naught, comes down and hits 1, and then it just stays there because there's this dynamic balance. Here, because there's these recovered compartments and they suck out everybody, and the susceptibles keep going further down, your R, effective R, even goes below 1, at which point your infected population starts decreasing. Okay? So here again, you can think about effective R. So the effective R, as I had mentioned, let's talk about that. I'll put that down also. The effective R, let me put, is R naught into small s, or large S by n. So in the SIR model, for any kind of spread, you need to start above 1, but then it comes down to 1, that's where the peak is, and then it goes down. By the way, this R naught equals 1 R equals 1 point is sort of related to what people talk about as herd immunity. You would have heard this, right? What does herd immunity mean? It kind of means that there are enough infected or recovered people around that if I might have an intrinsic R naught, a basic reproduction number of larger than 1, say 2, but because there are enough already infected, already recovered people, it brings me down to 1 or below 1, right? The herd immunity threshold is where it brings me down exactly to 1 so that I at most infect one other person, and therefore the infection just stays alive. Anything slightly larger than the herd immunity threshold, that means my effective R would be less than 1 and the infection would die out. So that's herd immunity. And you can think about herd immunity in all of these compartmental models, and it's very related to this R naught, or more specifically to this R effective. And in these simple models, you could even calculate it. You could, since we know what R naught is given the parameters, if you tell me beta and gamma, I can tell you what's R naught, I can tell you what's the herd immunity threshold, I can tell you where the peak will be, how many will be at the peak. I can also calculate, we don't have to do that, but you can calculate eventually how many will be recovered, how many susceptible might be remaining. All of that you can calculate. So, that's all the advantages of a simple model. And it gives you a certain kind of qualitative insight into the kinds of dynamics these diseases can have. But remember, there are always many, many assumptions. Not least that it's deterministic, not least that we've chosen particular compartments, that it's a well-mixed system, and all of these can be questioned. So when we come back from the break, what I want to take you through is the various ways in which people complicate these models because they actually want to make specific predictions about a specific disease. Okay, so far, this is just to give you a sort of a qualitative idea of what kind of things go into a compartment. Any questions? Otherwise, I guess we can break, right? This is break. Yeah, so herd immunity is just, it's the same, it's just a term used to describe this phenomenon that even though I might be very infectious, in a population where there's already infection has spread quite a bit, and there are people who are immune or infected, and so not so many susceptible people around, it can happen that even though I'm very infectious, the infection may not spread from me very much. And because there's already people who are recovered. So let's take an example. So let's say everyone here is susceptible, I'm infected, and I'm doing, say, 10 handshakes a minute, and I'm infected for 1 minute. In 1 minute, I recover. So in that 1 minute, I do, on average, 10 handshakes, and let's say there's a 20% probability that I transmit, right? So I would, normally, if all of you were susceptible, I'd do 10 handshakes, 2 of you would get infected. But now let's imagine a situation where 50% of you are already infected. Now I'll do 10 handshakes, but only 5 of you of those handshakes are actually with susceptible people. And 20% of that is 1. So I will only make 1 new infection. Now suppose it was even higher. Suppose it was just a little bit higher than 50%. Say it was 60%. So I would make 10 handshakes, 4 of you would be susceptible, and 20% of 4 is just less than 1. So very likely, so there's some probability I will infect you, but on average, I will infect less than 1 person, which means the infection can't spread. So herd immunity is that threshold. Herd immunity says there's just enough immune/infected people who are immune to further infection, already in the population that a new infection coming in cannot spread. So it's completely related to this effective reproduction number. Just remember, the R0 is a basic feature of the infectiousness of a disease, something to do with not just the disease, but also how we interact and so on, but the whole spread of the disease. It's something to do with, but in a situation where everyone is susceptible, and you're just talking about how 1 infection would spread in a large susceptible population. But over time, more and more people get immune, and therefore the relevant number is not the basic reproduction number, but the effective reproduction number, which is this. And as the number of susceptibles goes sufficiently down, you will always bring that basic reproduction number down to 1. At 1 is the threshold where infections can spread. So that's herd immunity. Now, depending on the model, that's where you may reach a dynamic equilibrium, or if you are in an SIR type model, you'll keep going further down and the infection will eventually stop. Does that make sense? Okay, yeah.